So first of all, I would like to summarize the NWPP system at Environment Canada that we have as of this year. So as you may know, we have 40 EnVar for both our global and regional deterministic prediction system. And we use an ensemble Kalman filter to generate an ensemble of analysis to both feed global ensemble prediction system and also to provide background error covariances for both the global EnVar and also the EnVar for our regional system. So we don't have yet an equivalent of the global EnKF at the regional scale. So for the regional ensemble prediction system, we just recenter the global, so the deviation from the global ensemble mean around the regional analysis to create our regional ensemble forecasting system. And we also do have a convective scale system running 4 times per day with a resolution of 2.5 kilometer, covering all Canada, so you can fit in Japan many times within this domain. But still, it doesn't have its own dedicated data assimilation system. We're just downscaling the 10-kilometer regional analysis onto this grid. So where we are going toward, previously I was putting a date, an exact year, so now it's more 2020-ish, is, well, we are going where most people are going, is to have hourly cycling system with the proper data assimilation system. So we want to have a 40 EnVar system producing hourly analysis at 2.5 kilometer, feeded by a dedicated EnKF system at roughly 10 kilometer that will also provide an ensemble of analysis for the regional ensemble prediction system. So what I would like to show you today is a prototype of that system. So it will be a simplified version, still with a 6-hourly cycling approach. And everything will use a model at 10 kilometers. So even the deterministic forecast will not be made at 2.5, but at 10 kilometers, the same resolution than the ensemble system, which is to do a mini experiment. And it also make a direct comparison between EnVar and EnKF possible. This is what I want to focus on today. So just to summarize how our limited 40 EnVar system works, so it's really based on the global version that we have with the following exception. So we use a spectral decomposition based on the Fourier approach instead of spherical harmonic to modelize the climatological B matrix and also the localization in the ensemble-based background error covariances. Localization was adapted, so we localize more in both the horizontal and in the vertical compared to the global. So we have half the length scale in the horizontal and a third of the length scale in the vertical. And we also apply hybrid background error covariances, and the weight have been tuned. So we put more weight on the ensemble part and a slightly less weight on the static part. As for the limited EnKF, it's also following our 256 member global version with the following exception. We have the same model configuration for all the members instead of the multiphysics approach. Additive inflation is still based on the global B matrix, but we have reduced the scaling factor, so the weight or the amplitude of the additive perturbation are slightly less. The land surface initial conditions are provided by the regional prediction system instead of the global system. And what is important to say is that in both the regional and in the global EnKF, we assimilate less observation than in the EnVar system. So for example, ground-based GPS, radiances from geostationary satellite, and SSMIS are not assimilated in the EnKF. And also there are many channels in both crea, AIRS, and EIZ that are not assimilated in the EnKF. And finally, the lateral boundary conditions are different. So the regional system is nested within the global system, and of course, the regional EnKF is nested within the global EnKF. So what I want to show you first is a comparison of the quality that you get between a forecast initialized by the RDPS 40 EnVar versus a forecast initialized from the ensemble-mean analysis. So I'm going to show you comparison in July, so summer, and January. So it's forecast over a full month, made twice per day. So you have a roughly 60 sample in a year. And it's shown using a scorecard approach. So how does it work? You have lead time ranging every 6 hours from 6 to 48 hours. And you have 2 sets of verification data, what I call altitude. So it's temperature and wind based on aircraft data, and humidity is based on ground-based GPS. And what you're looking at is relative differences of RMS error. So the RMS error of the red experiment minus the RMS error of the blue divided by that value. So when you see red triangle, it means that, blue triangle, it means that the blue here, the control, is better than the experiment. And the size of the triangle is proportional to the amplitude of the differences. And they are capped at 5%. And when the value exceeds 5%, you get a number. A number is appearing in the triangle. So here, 11 mean 11% of differences. And in altitudes, for wind and temperature, it's an average between surface and 100 hectopascal. And you have also surface. So this is a value with 2-meter temperature, dew point, wind at 10 meter, and surface pressure. So what you can see here is most of the triangle are blue, especially at short lead time. It means that the forecast from the RDPSE and EnVar are much better than the forecast from the EnKF ensemble-mean analysis. So we try to use very pragmatic approach to try to improve the quality of our ensemble-mean analysis. And what we've done is to test 4 flavors of recentering around an EnVar analysis that is based on this equation that was used recently in Peter Kammerer's paper in the global context. So it's very simple. So for every ensemble member, you want to recenter, you have the raw EnKF analysis. And you have this correction term, which is where C is just a scalar. And you have here the difference between an EnVar analysis and the EnKF ensemble-mean analysis. And what is very important in our case is that the background that we use to generate the EnVar analysis is the ensemble-mean forecast. So it's not a deterministic forecast that is used as a background. So you can do many things with this by changing the C. If you put C equal 1, then you have full recentering. That means that the recentered ensemble will have an ensemble mean exactly equal to the EnVar analysis. You can do what Peter Kammerer has called CMC hybrid gain. So you put C equal 1 for half of the member and C equals 0 for the other half. So in this case, you will change the spread of the ensemble, whereas it's not the case for the first one. It's also not the case for the third and the fourth configuration. So in third and fourth configuration, it's just using a coefficient which is not 0 or 1. So in this case, 1/2. So you put half weight on each ensemble mean. And when you use C equal 2/3, it's you put the mean will be a mix, 2/3 from the EnVar and 1/3 from the EnKF, the raw EnKF ensemble mean analysis. So first of all, I will show you the impact of these 4 flavors of recentering on the forecast from the ensemble mean analysis. And I'm going to show you first the impact of using full recentering versus no recentering at all, using again the same scorecard approach. Now the triangle are red, meaning that full recentering has big advantages, mostly at the short lead time, and it's decreasing with time, probably because the importance of the LBCs are growing with time. So the importance of the initial condition is decreasing with time. Sorry? Exactly, but forecast from the mean analysis and not the mean of forecast. See? So we integrate the ensemble mean analysis. Yeah. That's it. So what you can do also is if you average all the value in there for the upper error, you can get what I call a change in the quality index, which is here 0.2.32%. And you can do the same thing at the surface for both seasons, and then you can create a table, a nice table, showing all the results from all the 4 flavors tested. So you have here July, January, altitude, surface. Here we see the 4 values that we saw on the previous plot. And you can see that full recentering, well, all four flavors have big advantages over no recentering at all. And full recentering is slightly better in most of the season compared to the other one. But the differences are not that big. Now, what the first incentive of this was by improving the quality of the ensemble analysis. Can we improve the quality of the deterministic prediction system? Can we improve the covariance, the background error covariances that we provide to the 4D EnVar system. And unfortunately, the answer is not really. So here what you're looking at is the same changes in quality index for all the 4 flavors. So the control is 4D EnVar using the traditional or regular ENKF. And you can see that none, in all the 4 cases, you don't see a big impact. It's either slightly negative, slightly positive, or even perfectly 0, which is quite amazing. So unfortunately, there was no gain by recentering, it seems, on the quality of the short-term background error covariances. What's interesting is now is to see if we get a better regional ensemble prediction system. So for each of the ENKF, we picked 20 members out of the 256, and we generated 72-hour forecast. And I'm going to show you now scorecard as before, but they are slightly different because we are in an ensemble context. So now the differences is not based on RMS, but on the CRPS, so the CRPS. And this time, it's not for the altitude, it's not an average over level, it's individual level. So here you have wind at 100 hectopascal, wind at 250, zonal wind at 250, height at, geopotential height at 500 hectopascal, T minus TD, so dew point departure, at 850 hectopascal, temperature at 850 hectopascal, and the same surface variable. And you also have precipitation, so based on Breyer skill score. So for both surface and altitude, you're looking at relative differences of CRPS, whereas for precip is just because Breyer skill score is already a relative measure, it's just the differences of the Breyer skill score times 100. So again, when you see red triangle, it means that the red experiment is better, so full recentering improve the probabilistic score. And again, you can do the same thing, so average all the value to get a change in index and build a nice table like this. So what you can see again is all the approaches bring lots of improvement for both summer and winter, both altitude and surface. The CMC hybrid gain approach, so the only approach that changed the initial spread has a slight edge over the other approach. Not really in summer, but in winter, it's really like a 2-for-1 ratio compared to the other one. And it's interesting because CRPS can be decomposed into reliability and resolution. So I can compute the same change of index, but only using each component. So this is what you get when you base your index only on the reliability component of the CRPS. Then you see that CMC hybrid gain, the one that changes the initial spread, is outperforming everybody. But when you look at the change, only the change from the resolution component, no, it's not the one that produced the best forecast. It's a mix of full recentering or the hybrid gain where you give half of the weight to each ensemble mean. So, summary. Inserting various amount of information from a limited area EnVar analysis made here using as the background the ensemble mean forecast improves significantly our limited area EnKF ensemble mean analysis. And we saw that complete/full recentering provide the best forecast improvement. Unfortunately, one of the main goals of this was to try to improve the deterministic forecast, and it's not the case. It seems that using the ensemble mean derived covariances from the various recentered ENKF has no significant impact on the EnVar-based system. And all the recentered ENKF analysis improves slightly the performances of our original, not slightly, but significantly, the performances of our original MPS. And the so-called CMC hybrid gain approach, where we recenter only half of the member on the EnVar analysis, provided the largest improvement due to the resulting modification of the initial spread. So as you see, the results are mixed. So you might ask me, so what's the best approach? So far, I don't have the answer. Clearly, in terms of an ensemble perspective, ensemble forecast perspective, the CMC hybrid gain approach has an edge, but But you can ask, okay, because it's the only one who changes the spread. If I find another way to change the spread with the other approach, can I match the performances? So this is something what we will look at in the next couple of months. Thank you very much.
Thank you.